Another important skill or set of problems that you need to solve with equilibrium, dynamic, net forces, those sort of problems with Newton's second law kind of fall into this category called elevator forces. This is just some review of Newton's second law. So moving, not accelerating. This is another important thing to kind of just talk about again. So you can be moving with a constant velocity, and that's dynamic equilibrium. So in that case, there's no acceleration, which means there is no net force. So keep that in mind. When you have a velocity, that means acceleration is zero, which means there is no net force. Obviously, if your velocity is zero, you're at rest, then that means there's no acceleration, and again, no net force. So just kind of keep those things in mind. Again, some quick definitions. We talked about the normal force before. Tension is a force transferred through a string or wire, some type of a cable-like material. Your tendons can be considered, strings. All right, so let's start with this example, the 100-kilogram mass hanging from the ceiling. So what forces are acting on the mass? Well, we know we have weight straight down, so the force due to gravity, mass times gravity, weight. So in this case, it comes out to negative 980 newtons. But we also have the tension acting up on this object. So because there's no acceleration, there's no motion, there's no net force, then these things are going to be balanced. So sum of the forces equals zero. What are my forces? Well, we got the force tension going up minus the weight going down. They add up to zero. So the tension is equal to the weight, and it's positive, so 980 newtons. Now, if this object were moving with a constant velocity, either up or down, you would still have the tension equal to the weight. So next scenario. What if this object were accelerating upwards at 3 meters per second squared? Again, what are the forces acting on the mass? We still have the weight due to gravity going down. It's still negative 980 newtons. But we have a different tension pulling this object up because it's accelerating. We write our statement, identify the forces. So now to solve for the tension, it's going to be the mass times acceleration plus whatever the weight is. So 100 kilograms times 3 meters per second squared, 300 newtons plus 980 gives you 1,280 newtons. The tension has to be more than the weight. So another way to think about it, and I think this might kind of summarize it a little easier, is these elevator forces, don't F up, okay? The force up is equal to the mass times gravity, either plus or minus an additional acceleration. So if the acceleration is up, you're going to add that to gravity and then multiply it by the mass. It might be a little easier to do it this way because it kind of gives you one neat little equation. You're either going to add or subtract acceleration from gravity and then multiply it by the mass. So in this example, the object is now accelerating downward. So what's going to happen? Again, the weight is still down at negative 980 newtons. The force from tension is still up. That's the force up. But it's going to be less than before. We can do our statement, sum of the forces. In this case, it's equal to negative ma because this acceleration is down. When we solve for tension, we get ma minus the weight. So it comes out to 680 newtons. Another way you could do it, F up equals mass times gravity minus acceleration. So we do 9.8 minus 3, take that answer, which ends up being 6.8 times 100 kilograms, and we get 680 newtons. Okay, so now let's imagine we're on the elevator and we're standing on a scale. If the elevator is at rest, or if it's moving at a constant velocity, either going up with a constant velocity or down with a constant velocity, we would feel normal weight. Okay, everything would be balanced, and the force up would be equal to the force down. So the force the scale pushes up on me with would equal the force I push down on the scale with. In this case, the force normal would be equal to the weight of the person. This would be your true weight. Now, what if the elevator is accelerating up? What happens to the scale reading? Well, the scale reading is going to be greater, just like before where the tension increased. Well, the scale reading is going to increase. So that would be the force normal pushing on the person. Your apparent weight would feel greater. Okay? So if you're on that elevator and it's accelerating upwards, you would actually feel heavier. Now, what if the elevator is accelerating downward? Well, just like before, the tension is less. So then that means the normal force is going to be less on you. Your apparent weight will be less. You will feel lighter. And it kind of makes sense. It's like you're trying to stand on this scale, and the scale is accelerating away from you, downward. So you can't be pressing on it with the same force. And what if the cable breaks on the elevator? Well, now you're in free fall. Everything inside the elevator is in free fall. It's all accelerating downward at 9.8 meters per second squared. So this is what we think of as a weightless situation. Okay, we cannot press on the scale. The scale can't press on the floor of the elevator, so you can't actually create any sensation of weight. This is what astronauts feel, or the International Space Station. These things are in constant free fall around the Earth. Okay, they're falling, and their fall and the pull of gravity is matching the curve of the Earth. So they're in constant free fall, which is the weightless environment for them. And then this is where, the thrust, okay, from the space shuttle or rocket or whatever, we have the weight down, but this thrust is so great to try to accelerate the astronauts into outer space. It creates these extra G-forces, okay, multiples of gravity on the person, which is why they have to lay down like this. If they were standing up, that would be a lot of force on their spine, and they'd lose blood, pass out. When they lay down, their body can handle it a little bit better.